Hello everybody. Today we will be talking about p-type controller design via Bode plots. Basically, we did see the Bode plots before. This is a frequency plot. You can use this given transfer function here, and if you plug in s equals j omega, then you would get a complex number that's depending on a variable omega, which is basically a complex valued function. And if you change omega in a certain interval, then you will get a complex value, a continuous complex valued function, and you will have a real part and an imaginary part. If you convert this Cartesian coordinates into polar coordinates, then you can get the gain and phase that will change versus the frequency. And the Bode plot shows exactly these two plots, the gain and the phase plot. And from here you can view this system as a filter that depends on omega, and you can then examine for which frequency what properties are present, and you can then see and conclude what the output will look like. Because this is a frequency method, the practical correspondence here is that you have a system. This can be a black box, this can be a system that you know the model of, and the thing that you're doing is basically you're applying a sinusoidal wave as an input with gain 1 and phase 0. And since this is a linear system, what happens is that the sine wave will get modified, and the only change that will be happening is basically the phase and the gain. And you can directly examine the transfer function in order to see what those will be for each frequency. And looking at these plots, we can conclude some results. We can analyze the plot and come up with certain information about the transfer function or the system. Now here we will see how to calculate the stability interval using the root locus plot, which should be very easy for us because we did this a couple of times. And then we will compare it to the Bode plot version, because if this is a system, I should be able to get the same information using different methods, and we will see if this is the case here. Now the root locus plot is given here. This is the positive root locus of the system. Since this is a third order system, you can see that we have 3 poles, and it seems to be that all the poles are on the real axis, and they coincide here and move so that they will approach the asymptotes here, and the other one is here because there are 3 poles, no zeros. We can easily see that the asymptotes will be 60 degrees, minus 60 degrees, and 180 degrees. So, and if we choose these points, we will see that the pole zero map or the pole spread in this case, because we don't have a zero, looks like this here. And if we are examining the negative root locus, then we see that the crossing here is basically on the real axis through the origin, basically. So if we solve this, we will see that there will be a certain omega to this solution, and there will be also a solution for omega equals 0. And we can see that these are the limits. So if I want to get an interval, I have a negative k value that represents this pole spread, and I have a positive k value that represents this crossing, basically. Now, if I use the root locus properties here, I can see that the arguments of the poles, namely the angles of poles, will be summed, and the difference between the angle, sum of the angles of the poles and the sum of the angles of the zeros. Because I don't have any zero, it will be much simpler. The only thing that I have to look for is that I have a sum of 180 degrees for all 3 pole arguments. So basically, I know that this will be contributing 180 degrees here, because we look for the counterclockwise angle here, and then there will be a certain angle from here to here and from here to here. So basically I have to sum these 3 angles and I have to look for it. So you can see that adding the angle of the pole that is at -1, which is this one here, and at -4, which is this one here, and then -6, which is basically this one here. So keep in mind that I'm taking the open loop positions, and then I'm looking for this design point or this destination point here. So these should satisfy this condition given here. And you can see what I mean by this. -1, -4, and -6 are the open loop poles, and I'm looking for j omega, the crossing where omega is the unknown here. So if you look for the slope of this line here, represented with -1, you can easily see that this distance is omega, this distance is 1, so the fraction here gives me omega, so the tangent of this angle, basically this here, I'm trying to show it with the mouse, will be omega. And if I use -4, you can always take this distance. You will always take this distance, and it is equal to omega, because I don't know what exactly this distance is, and I'm looking for it. But I know the real distances here, or the distances on the real axis. So since this is y divided by x, I can see that everything will be every angle will be, or every tangent of the angle will be using omega divided by 1, omega divided by 4, and omega divided by 6. So I have to take the inverse tangents, and I have to apply it to this equation here. If I do this, I get this 3 inverse tangent sum that will be equal to -180 degrees. If I take the tangent, I will get 0 here. So in order to solve this, I will move on here. You might use some trigonometry here, because we have a and b, and the sum of tangent a and b can be calculated with this. So there are certain multiplications, and since this is a 3 sum, you have to look for tangent a plus b plus c. A method can be, you can work this out by assuming, let's say, this as a and this sum as b. Then you have tangent of a plus b. You have to use the trigonometric identity here. And once you've done that, you have to repeat the process with, let's say, x and y. So since this was b, this is equal to b. You have to take the tangent again, and then you will have basically to repeat the same thing in order to solve a 3 element tangent here. So tangent a plus b plus c. So if you work this out, you will get this fraction here. You can check it out. I'll leave it up to you. And if you try to solve this, it is sufficient to look for the zeros here, or this should be equal to 0. This should not be equal to 0, basically, but we are only concerned with the numerator here. And if we work this out, we will see that basically we have omega 0 and we have 5.831. So of course you can use MATLAB and you can click, but sometimes you need to know how to calculate it by hand, because it may be a classical an exam. So if you don't have MATLAB available, then you should know how to do it. It's not that hard to see what it is, because if you know the angle condition, and since this is a all pole system, this system has no zeros, it's pretty much an easier version of the general case. Now, once you've done that, you can see that this is where it crosses. So then you can use the gain condition, which looks like this. You have to look for every distance of the pole, multiply them, divide that by every of the whole multiplication of every distance of the zero, and then you will get basically the gain here. Since we know what omega is, we can plug the omega value here. I have seen that omega squared was 34. Maybe plugging in here 34 gives me 35, 34 plus 16, and 34 plus 36. If I use omega 0, these omega squared terms vanish, and it will be 1 and 4 and 6, so the multiplication gives me 24. Keep in mind that this is the negative crossing, so I may have found it that it is 24, but this is on the negative root locus, so I have to include minus by myself. And if I do the necessary calculations for omega equals 5.831, then I will get 350. So I can then state that my stability interval is between 24 minus 24 and 350. There's also a certain code that I've written to find the distances, and then I'm taking the product of these distances. So you can look at this and work it out yourself, or you can just look here and make the same. As far as I remember, I'm not sure, this code should carry out the sizes automatically, so it's actually not that hard. You have a certain frequency, and then you look for a distance. Since this is j omega times 1, which means that I will generate an array of j omegas that has the same size as bs, so I can use this difference here, and then I'm taking double to be sure that this is basically a double value, and there's no omega involved. And I do this for the distance of poles, distance of zeros, then the product of absolute values dp and absolute values dz. So this will give me basically k0. And for 5.8, I repeat the same with this second omega. And as far as I remember, I am solving here. I'm defining my same distance, but this time I have a symbolic variable omega. So if I take the tangent of the sum of the angle of poles, I'm basically implementing the same thing here that I've shown you. So I'm implementing the same thing, and I'm letting MATLAB solve it. You can also work out this one. You can see that, but this code will automatically, hopefully, generate the solution here for omega, and I have 2 omega values. So that's the root locus part. You can also, as I've said before, you can also go ahead and check it by just plotting the root locus and clicking here. But I've shown you the trigonometric version and how to solve it basically by hand. So then we will use Bode Plot. Now the Bode Plot is very important since it gives the same data, and it provides you the interval for any Bode plot. Now keep in mind that the first version or method that we've used is the root locus method, and the root locus method needs a mathematical model. It needs to it wants you to define the poles and zeros and the gain of the system. You have to know exactly what they are. But in the Bode plot, if you have a Bode plot and you don't know where it comes from, or you don't know the system model, it doesn't matter. You can just use the Bode plot to come up with a gain or an interval for this gain. So this is the power of Bode Plot, but it makes also sense that if you have a mathematical model, you should go ahead and use the root locus method. If you don't have an idea about the model, you couldn't model the system with a transfer function, then you should try to acquire a Bode plot and then use that for analysis and synthesis. Now, this is the Bode plot of the system. You can just use Bode and in MATLAB and provide the transfer function. It will give you this plot here. Now, since we are plugging in s equals j omega, we look for k times g divided by 1 plus k times g. And then if you want to look for stability or even instability, instability happens when you have a division by 0, because it will give you infinity, and this infinity corresponds to an output that is not settling down to a certain value, that doesn't have an equilibrium. Now, even if you provide a bounded input, your output will be, since there is a division by 0, your output will be tending to infinity. So we are looking for that point, and for that point we have to look for the characteristic polynomial, or the denominator of the closed loop system, where we plug in s equals j omega, and it should be 0. And since kg divided by 1 plus kg is the closed loop, we can easily see that 1 plus kg should be equal to 0. Now, this implies that k times g is equal to minus 1. And therefore, in the frequency methods, this minus 1 is most of the time very important for us, because we look for the certain parts of this minus 1. Because we are in the polar coordinates, or we did convert it into polar coordinates since the Bode plot has a gain and phase plot, this minus 1 can be also converted in the polar form, where you have gain 1 and in a phase of minus 180 degrees or 180 degrees. In this case, since we are in the interval of 0 minus 300, we are looking for minus 180 degrees. And we look at this point, since if this is equal to minus 1, if I combine the phase and angle and I will get 1 and minus 180 degrees, then I will have instability. So that's the critical point. Now, of course, a system does not have to satisfy both simultaneously. So the gain can be 1, but the phase can be a different value than 180 degrees. Or the phase angle is minus 180 degrees, but then you couldn't satisfy the gain condition. The gain should not be equal to 1. It doesn't have to be equal to 1. So therefore, you have the gain of your controller and the multiplication of them, so k times g, should be equal to 1. That can be equal to 1. And we're actually looking for the point where the phase angle is minus 180 degrees, and I have a certain gain. And how much gain can I add here so I will reach 1? That's the question here. And you can see that we are in the interval of 0 and 0.04. So if I multiply this, let's say if I'm somewhere here, if I multiply this by 100, since this is not decibels, this is just the gain value here. I've modified the Bode plot to simplify certain things for you. If I have let's say this point, if this point is 0.01 and it has angle minus 180 degrees, then I can multiply this with 100. If I multiply this with 100, or if my controller gain is 100 exactly, then I will have 1 and minus 180 degrees, which is instability, which is the instability point. So, of course, it's a lesser value. This means that I will have a higher value for my k, since this Bode gain here will be modified so that this point, this critical point here, passes through the gain 1 and the angle minus 180 degrees. So this is very important. If you understand this basic concept here, then it is very easy to look for that. Now let's see what the actual steps are. So we're looking for 180 degrees, and if I plug in s equals j omega, I get a complex valued function that's depending on omega and has a real part and an imaginary part, basically this one here. So you can use the conjugate here, but it's not that necessary. So if you look for the phase angle, you can see that this is minus tangent because this has angle 0, this has tangent something, and the difference will give you the angle here. So basically minus the inverse tangent of the imaginary part divided by the real part. You can see that this is basically automatically defined. And then you have the inverse tangent of this 180 degrees. If you take the tangent, you will get this, and this is equal to 0. And surprisingly, you have the same equation as before, because in the root-Locus method, you've seen that we had a certain tangent, and this tangent had the same structure up to this point. We did some different calculations, but at the end we did get this here. So this means that we will get the same frequency as in the root-Locus method. So they have basically the same data in them. But here we're looking for minus 180 degrees, and this is basically the same here. The only thing here is that we are using the frequency domain, so we don't have to sum or multiply something. We have directly the term based on this fraction here, and this minus 180 degrees was the same condition as here. We did have the same here. So, and this relates basically to the frequency method, because the arguments in using the complex values, since this is the denominator, this is the numerator, you can work this out, because you have to take the difference between the numerator and denominator, and it will give you basically the same. You can probably prove this here or the other one by using the other method. So they are relating to each other. Now, once I have this, I can then go ahead and use again the transfer function itself, where I've plugged in s equals j omega, and directly calculate this gain here. And I know that this multiplication should be equal to 1. And note that I have k here, so I'm looking for the positive value. So this multiplication should be equal to 1, with omega being 0, or 34 minus omega squared, so omega squared being 34. So if I plug it in, if I use omega 5.8, I will get 350 approximately. And if I plug in omega 0, I will also get a value for k. But I have to check again what the angle becomes here, because omega 0, if I plug in omega 0, I should somehow know that this one is the negative bound, and this is the positive bound. So you have to basically check again what the body looks like, or what your calculations will give you, because if you're looking for the point where minus 180 degrees is satisfied, you will get the positive one. If we have 0, because k will be negative and this negative one has minus 180 degrees, then you should then you're dealing with the negative bound. So approximately 0.04. The inverse should give you something around 24. So basically, the second one of the critical points passes through minus 180 degrees. The other one, the negative root locus part, or the negative bound for the controller, should pass through 0 degrees. Okay. And then there's a code for this. You can use the transfer function, logarithmic scale. I'm converting this into the symbolic toolbox. You can do it manually, or you can just write a function that converts any transfer function into a symbolic expression. And it's up to you. Then you substitute j omega, and then you look for you just plug in the interval. You get the gain and phase. You have to do some modifications here. Especially for the angle, because a tan 2 is a function that uses the imaginary and real parts and gives you 4 quadrants angle, but the angle is between minus 180 and 180, so you have to adjust it so that it will be between 0 and 360. And then since you're searching a point where the phase angle is a certain value that you're looking for, namely minus 180 degrees, you have to look for the closest point here. I'm not using an if statement, or I'm not searching where I take minus 180 degrees is equal to phase, because that may not be available, but since it should not be, it doesn't have to be exactly minus 180 degrees, since this is a numerical calculation. It might have an error in it. So the safest way is to look for the closest point here, and that can be defined by an error vector, and you can minimize this error. So basically, I'm doing this here, and once I've acquired that point, I display the omega value, the gain at that point, and the argument at that point, and I can easily look for k, because this is the inverse of the gain value at that point. And this kind of concludes our discussion on the p-type controller design via Bode Plot compared with the root locus. Now I have another PDF another lecture note, because they are closely related, or they are basically in the same topic, I have decided to cover them both in this lesson. So this was part 1 here. We did look for the root locus and Bode plot, and we've seen that we can use the data on a system to analyze it, to attack it from different angles. So here we will see in this part 2, we will see the effect of adding a pole or a zero on the stability of the system. Let's say we have a third order system, and I'm not sure if it's the same system. It seems to be the same one. Okay, that's even nicer. So we have the same system here, and we will look for the p-type interval, and we did that basically, and we will see what will happen if we add a zero at the origin, and what will happen if we add a pole to the origin for the system. So basically I'm multiplying this with s, or I'm dividing this by s. So basically I'm adding a zero or a pole. And we will see what the stability for the p-type controller will be. Now, basically, we've seen this part. We've already seen that it is between -24 and 350. And we need frequency values. So let's say we add a zero at the origin. Now look at this root locus here. You're adding a zero at this point. So this means that this pole will approach that, and these will approach each other, as far as I know. And you can see that this is exactly the case, because you should remember that plotting root locus, those rules will give you this information. So this approaches this one, and then we have these meeting each other, and then tending to positive 90 degrees and negative 90 degrees asymptotes. And then the negative root locus becomes like this here. We can also see that there's a crossing here. So if I look for the interval, if I'm multiplying with s, I will get this, and I look for the whole stability here. I can also use directly -gs and gs, or I can use this method here to get the solution here. So I get that the frequency is 1.4771, and my value for the negative bound becomes -31.8. And there is no positive crossing. So because we have a zero at the origin here, this pole will approach this zero at infinity. So basically, the upper bound for my p-type controller, the stability upper bound, will be infinity. And since these are tending to the asymptotes, they're moving closer and closer to the asymptotes, they never try to get on the right half plane. And since all three poles will stay on the left half plane, I will have no stability issue on the positive side. So if I have a positive p-type controller, I can choose whatever I want as gain. It will be stable. Of course, I'm not going to choose any controller, because I might have time specifications or some considerations for the closed loop, some objectives, but the whole interval, the whole positive interval, is available for me as a controller that stabilizes the system. Now, for the negative part, we have a crossing. Basically, two poles cross the j omega axis. So I don't have infinity here. I have a certain value, and I can see that this value is also a little bit extended. So based on this, and based on this system only, I can say that adding a zero to this system increases its stability interval. And the logical explanation for this, or this makes sense because the more poles you have on the left half plane, or the higher the degree of your system, the harder it will be to contain them on the left half plane, to restrict them, or to hold them on the left half plane. Because if I have less poles, then I have less effort, or I need less effort to hold them, or to play to not let them cross to the right half plane. And we will see that in a minute. And adding a zero at the origin, for this system especially on the positive side, has or simplifies this process, because I know that in a root locus plot that all the poles tend to the zeros. All the open loop poles will move in the closed loop, so that they will eventually reach the zeros. So I might have finite zeros and infinite zeros. These asymptotes are infinite zeros, basically. So these two on the left are approaching the infinite zeros, and this approaches the finite zero. Before that, we didn't have any finite zero, so we had infinite zeros at those points, at these points here. So they were approaching them. But if I place a finite zero at this point, this will reach this, and the infinite zeros will become here. So basically, the whole movement will change, and basically, since this ensures that one of the poles will approach the zero, I'm basically preventing one pole or the crossing of one pole. So it is easier to contain two poles on the left half plane than three of them, because of the angle condition and the asymptote angles. Now, what will happen if I add a pole to the system? Now, you can see now that adding one more pole will change my angle of asymptote, and you will see that this angle decreases the more poles I have, because it is 180 divided by some linear relation on the degree of the system. So the higher the degree, the lesser the angle here. So it will be more likely that the poles try to cross on the right half plane. So adding one more pole creates this interesting structure where both of them cross to the where both of them are crossing, so that they will become unstable. Before that, before even adding a zero, I did have the same thing, but here my angle is decreased, so most probably my upper bound will become a lesser value. So let's see what the upper bound actually is. It is 69.42. It was 350, so it decreased dramatically. And I can see also that omega 0 gives k0. So there is no negative bound, because I've placed already one pole at the origin. So having a pole at the origin is not that desirable, because on the negative side it will directly tend to the right half plane. So even if you had this structure here, because you can see this is tending to the left and these are going upwards and downwards, these are not trying to path the j omega axis or cross the j omega axis, but I have this problematic 1 divided by s term, which is not stable for the right for the negative value, since it will move on to the right. So this gives me 0 bound. I had minus 24, so this is decreased. And then this is leaving the left half plane. These poles are leaving the left half plane earlier than the previous version, because it has not that much distance, and it has a more aggressive angle, so that it will more likely cross the j omega axis earlier. So I can see now that adding a pole will narrow down the interval, and adding a 0 will most likely help me out. So a better thing here is to consider adding poles on the left half plane, but I've looked at the margin, because if I place something on the origin or j omega axis, it's more likely to be at since this is the critical point, it will be the worst case for most of the time. So if I'm adding a pole, it is more difficult to stabilize the system. If I'm adding a zero, this will most probably help me out. So why did we see the effect of adding a pole and a zero? Simply because if you're trying to design a different controller than P-type controller, because remember that the P-type controller is just a gain, a static gain that doesn't have dynamic behavior. It's just looking at the error and multiplying it with a certain value and apply it directly to the system. Now you might want to add some dynamic behavior to your controller, which means basically you're adding a pole or a zero to your controller structure. And eventually this will be added to the system because the closed loop consists of the controller times the system and its feedback structure. So we see that adding a zero and a pole will basically alter your system, and adding a pole has an effect that we've examined here. Adding a zero has a different effect. Now, if you consider a PI controller, the PI controller adds 1 0 somewhere on the complex plane, but most probably on the j omega, on the real axis, because if you want to have a realizable system or a system with real coefficients, then if there is just one pole, that should be on the real axis. The PI controller adds a 0 to the real axis. It can be on the left side or the right side, or it can be at the origin, and it adds exactly at the origin a pole. So adding a pole on the origin will basically narrow down your solutions. But since you're then adding a variable 0, what happens is basically you're trying to choose a certain point so that you have a better design opportunity. PI control is basically looking for a place for the 0, since the pole is fixed at the origin and you have the system, and then choosing a gain. So there are 2 steps to design a PI controller: place a 0 and then choose a gain. So if you do that, you already have to add the pole at the origin and you will be good to go. For the PID controller, basically, you have 2 zeros and a pole at the origin. You can place the zeros on the whole complex plane at this time, because you have 2 of them, and you have to place a pole to the origin. And that's it. You cannot change the pole. So it has more freedom because you can place more zeros, and you can basically increase the stability of the system, since adding zeros is a better idea than adding poles. So in the PI controller, think of this as you're adding one pole that narrows down the stability, but then you're compensating that with a 0 so that your effect or your closed loop behavior is as you wish. And with the PID controller, you can even increase the stability even more, since you have 2 zeros. And I can generally say that adding zeros increases stability. Adding a pole at the origin will decrease the stability. So basically, you're trying to add 2 zeros, and you have the pole, you choose a gain, and you're good to go with the PID controller. There are also different structures like the PIPD controller, where you use the PD controller, place the 0, but the 0 doesn't affect the system, and it's more likely a PI controller with more freedom. So basically, these topics are the topics of control system design. And this lecture is more about programming techniques in control than control system design. So this will be the ending point for the laboratory sessions, because we have tried to learn how to use MATLAB, the symbolic toolbox, the control system toolbox, so that we're able to attack a control problem if even if it's analysis or design. And in terms of design, we've seen the p-type controller design. So go ahead and watch these videos again and again if you're not secure with your MATLAB symbolic toolbox, control system toolbox usage, or if you want to repeat some of the control aspects that we've covered here, because it's really important to have a nice base knowledge on programming techniques for control. So this lecture, this whole lecture is more about giving you a base, so you will have less problems in the control system design, and you will be able to adapt to the control system design lecture even more, since using MATLAB nowadays is very important and essential, and these some theoretical aspects, reviewing them is essential too. So hope that you did learn one or two things out of these lessons, and hope that you have improved your skills by trying to follow these lessons. Okay, that's basically it. See you in the next lessons and lectures.